Welcome back. In the last couple segments, we look at different queuing systems, but all of these systems we assume to have Poisson arrival, and also the departure is departure rate or the surface time is actually exponentially distributed. Or simply, we can just think of like the departure processes like Poisson. And however, if the departure process is not Poisson or like the surface time is not exponentially distributed, then apparently we cannot draw the state diagram as what we did previously and do that kind of very precise analysis that we get all the statistics of the number of packets in the system, even what's the probability to have that number of packets, and basically all the high statistics can be derived in previous cases. But if the departure process is not Poisson, as I said, it's something else. For example, it's deterministic. And then we cannot use what we did, the trick we did like previously. However, in some cases, we are able to do something. And for example, for the case of MG1, G here refer to the general distribution, general departure. There's a famous result known as the PK formula that's by authors here that I don't know how to pronounce exactly. And the formula is basically given by this: the average wait time is just equal to lambda times x square bar over 2 times 1 minus rho, where x bar is just the average surface time, therefore equal to 1 over mu, and x square bar is the second moment, or the x square, the expectation of x square. Rho as usual is just lambda over mu. Lambda is the arrival rate. So let's show this PK formula here. To show this, what we need to do is we need to introduce a concept known as the residual surface time. Residual time. Let's call it residual time. Just call it residual time. So what residual time is basically just think of like at any particular time, and I want to ask what is the remaining time for the packet that is currently served to finish being served. So it's a little bit mouthful, but RT here is the time, that remaining time, very ugly handwriting, remaining time for the packet being served will exit the system. Let's say that. So and also we will assume that if there's no packet in the system for the moment, then nothing is being served at the moment, then the residual time will just say it will define to be 0. So let's say now if at the beginning there's no packet in the system, and then let's say there's an arrival, a packet arrive, and let's say the packets will be served like with a surface time like x1. So after x1 period of time, the packet will get out of the system. And therefore, like this, if you think of like at this time t here, this t plus x1 here, at time t, we will have like x1 time more for this packet to get out of the system. Therefore, the residual time at t will be simply x1. And of course, like, as t progresses like t plus delta at time t plus delta, the residual time will be delta less, will be like x1 minus delta here. And similarly, at t plus 2 delta, the residual time will be x1 minus 2 delta. Then you can see apparently this should be a straight line. It should be just a triangle here. If you look at the residual time. Now let's say we have another packet coming in here. And the surface time for this packet is this x2 here. So then the residual time will be have another triangle like this. And let's say at this moment there's another packet coming in. Therefore, at this time, the packet will be immediately, okay, let's say there's a packet coming in here, but this packet coming in won't affect the residual time at this moment because we only care about the packets being served at the moment. So therefore, it doesn't affect the residual time. But let's say this packet needs like x3, this is x2 here, this packet needs x3 period of time to get processed. So immediately at this time, when the second packet exits the system, the third packet will be served immediately, and therefore, like, let's say there's an x3 here is the residual time. I mean, once the packet 2 exits the system, the residual time will jump to x3, and so on and so forth. x4, x5, and so forth. Now, with this residual time defined, let's think of what was the wait time. Let's define Wi as the wait time for the I arrival or I packet. Let's use packet, it's easier to say. What's the wait time for the I packet? The wait time for the I packet will be, there will be two components. One is, it will be simply, okay, equal to the residual time. Let's call this Ri here is the residual time when I packet arrive. Because when the I packet arrives, it needs to wait for whatever being served have to be finished serving. And then we need to add the wait time for whatever in front of the I packet. So the wait time will be like the sum of the service time of the packets in front of it. So let's say there's like nj packet in front of it. Or maybe I can just write, it will be xi minus 1 plus xi minus 2 xi minus ni. So there is ni packets in the queue when the I packet arrive. Okay, all of this makes sense. Now we will do some approximation here. If we try to do the average of both left hand side and right hand side, so we do expectation of this left hand side and expectation on the right hand side. So expectation of left hand side will just get the average wait time, and expectation of right hand side will get what? It will be like, what's the average number of packet in the system? That's basically nq. Sorry, not in the system, in the queue. Average queue times the average service time Okay, so this part we can really approximate this as like there will be on average there will be n-cube of them, and each of these components on average have like x bar so long, so big, so therefore like on this thing take an expectation will be just n-cube times x bar. Now what's the expectation of R here? I will just write this as R here. So what we need to find is what's the expectation of now, this the residual time. There's some unknown we need to find. But what is this? Maybe I'll use here. Go back to here. I can erase some of this and then just use the space here. So R will be just equal to, if we think of that, it should be just equal to the integral of RT dt from 0 to, let's say, a tau here over tau for some big tau here. Also, like probably we should take tau to some limit to infinity, but at the moment we just fix some tau here. It should be like this, right? It basically like we kind of like the average R will be just we find all the area underneath this curve here, this R curve here, and then like we just divide by the length of this tau here. And this integral is basically just the area underneath will be just sum of this triangle, and each of this triangle will be just have size x. Okay, the first one will have just, it's just an area of a triangle, therefore it's just x1 square over 2 plus x2 square over 2, so on and so forth. And how many triangles will we have? Let me just define that there will be empty triangle, where empty is basically, or like I should say m tau because I use tau here. M tau is the number of arrival within tau, or number of arrivals before tau, and then like okay, and then let me just write a little bit here using a summation, or maybe actually I don't even need that. So let's just stop here, use this same thing here, and what I can do is like for this same expression I can divide m tau here but multiply m tau here, but m tau over tau is just was the number of arrival over a period of time. That would be just the arrival rate, that would be just equal to lambda, therefore the first term is just lambda, and the second term is really computing the empirical average, average of the, or I should say empirical expectation of x squared here, right? So therefore like it should be just equal to expectation x squared, or like lambda x bar squared. Of course I have an over 2 here, so I need to over 2, so it's equal to that, and therefore R is just equal to lambda x bar squared over 2. So I have W equal to NQ x bar plus lambda x bar squared over 2. And of course the x bar here is actually just equal to 1 over mu here, What's NQ, by the way? NQ is actually related to W, right? By Little's theorem. By Little's theorem, NQ should be just equal to lambda W there. So therefore we have lambda W mu W plus lambda X squared for 2. And lambda over mu here is just equal to rho. Therefore we have 1 minus rho W is equal to lambda X bar squared over 2. And we put this down, then we have the Little's theorem here. And actually we can just do some example first, just to verify what we did is correct. For example, like take a MM1Q, let's say MM1, and X bar square is equal to 2 over mu square, I believe, and therefore like W is just equal to lambda over mu square 1 minus rho. Yeah, and you can verify that with the MM1 that we studied earlier, that this should be the correct expression. Let's do another example. Let's say MD1, this is deterministic, and in that case X again is just 1 over mu and X bar square, because like mu now is constant, like I mean X is actually deterministic. X is just 1 over mu, therefore X squared is 1 over mu square, and so therefore like W in that case is just equal to lambda over 2 mu square 1 minus rho. Actually, the wait time is kind of smaller than the MM1 in this case, and the delay is just equal to W plus 1 over mu.